Hi, I'm Jonathan Bayuna Sanchez. I'm currently taking Math 141 of Section 3 discussions in the semester of spring 2022. And currently, I'm going to talk a little bit about the Gauss-Jordan algorithm. And right before we hop right into it, we definitely want to have some background information to really understand this topic. And so let's get right into that. So what are we going to really need to know for the Gauss-Jordan algorithm? So we definitely know that there's going to be a bunch of system of equations that represents real-world scenarios for either land usage, games, and not very surprisingly, engineering, of course. And we're going to use a matrix, which you could use for systems of equations. Right over here, you could represent this with in matrices, and also to the 7 and 4 over here as another matrix. And so in our specific case, we definitely want to focus on the augmented matrix where we're going to be able to combine these two matrices into something looking right over here. You can see right on my cursor to the right, where we have a 2 by 2 with now another 2 by 1. And so what are we going to do with this? We're going to have a row. We need to understand the row reduction echelon form, and where we're going to have as a finalized as a identity matrix, as in the case of a 2 by 2, 1 0 0 1. So and that is equal to the vector for the constants. And to get to that point of the row reduced echelon form, we're going to need to be able to swap rows with each other, multiply rows by scalars, and then either subtract them by scalars with other rows. And so why would we need to actually use the Gauss-Jordan algorithm? What is the purpose? And so two main things so far. We definitely want to solve systems of equations representing those real-world scenarios. In the case where we have ax equals to b, we want to find the x vector or the matrix in such that the ax will be the one solution equal to b. And another major property, if we want to find the inverse of a matrix, if we can even find the inverse, is A times its inverse is equal to the identity matrix. And so how could you actually do this algorithm? So as a few of the techniques mentioned beforehand, if you want to solve for ax equals to b using the Gauss-Jordan algorithm, we're going to have to turn these two matrices into an augmented matrices, row reduce until we have pivots, and then finally work our way backwards when we have the known variables and plug them back to the unknown variables into the system that we have. And the second part, that when we want to find an inverse of a matrix, when we want to know if it's invertible, is we turn into the augmented matrix. The left side is going to be our original matrix, and the right side is going to be the identity matrix. And we're going to row reduce it until we basically have the left side is going to be the identity matrix, and the right side is actually going to be resulting into now the inverse of the original matrix we started with. And so sounds a little cool. Sounds like it's actually something a little bit complicated, but actually what could we even use it for? So here I have three generic concepts that we could actually use it for in general real world scenarios. Here we have circuits where we could solve for complex systems and trying to find maybe voltages or currents, or even physics where you want to identify the velocity, accelerations when you have a bunch of kinematic equations, or even day-to-day operations where you need to optimize for a solution. In the case for farmland, you want to maybe segment that off. And so, okay, talked about these scenarios, but now let's actually get to a system where we could actually show you this real world scenario and how we could actually solve it. Example up here where we would want to find all three currents, and the system we're left with is this right here. And so the very first step we would do in this case scenario to ultimately get our row reduced echelon form would be R1 is equal to R1 divided by 6. We would have 1, negative 6, 1, 6, negative 1 half, 10 divided by 3, negative 4, 1, 7, 16, 0, 1, negative 1, 2. The next part, what we would do would be to have row 2 is equal to row 2 plus 4R1. We're left with 1, negative 1, 6, negative 1 half, 10 divided by 3, 0, 1/3, 5, 88 divided by 3, 0, 1, negative 1, 2. The very next step, what we would do would be to multiply our 2 by a factor of 3. So what we would have is 1, negative 1, 6, negative 1 half, 10 divided by 3, 0, 1, 15, 88, 0, 1, negative 1, 2. The next step would be to have R1 is equal to R1 plus R2 divided by I6. And that would leave us with 1, 0, 2, 18, 0, 1, 15, 88, 0, 1, negative 1, 2. The next step, what we would do in this scenario, would be to have R3 is equal to R3 minus R2. That would leave us with 1, 0, 2, 18, 0, 1, 15, 88, 0, 0, negative 16, negative 86. And then next we would do R3 is equal to negative R3 divided by 16, 1, 0, 2, 18, 0, 1, 15, 88, 0, 0, 1, 43 divided by 8. Second to last step, we would have R1 is equal to R1 minus 2 R3. That would leave us with 1, 0, 0. We have our pivot there, right here. 0, 1, 15, 88, 0, 0, 1, 43 divided by 8. And then finally, R2 is equal to row 2 minus 15, row 3, leaving us finally with 1, 0, 0, 0, 1, 0, 0, 0, 1, 29 divided by 4, 59 divided by 8, 43 divided by 8. And these would be our currents for I1, 2, and 3. Okay, and now that we solved that, let's actually hop into a scenario where it might not actually be the Gauss-Jordan algorithm may not actually be the hero that we need, or it doesn't even work at all in the scenario. And so let's see that scenario. First, a very easy step we would have to row reduce this would be to have R2 is equal to R2 minus 3 times R1. And what that would leave us would be 2, 4, 1, 0, 0, and 0. Okay, get anywhere closer to our solution. So we would still have something like 2x plus 4y is equal to 1. But we still have two unknown variables that we never actually solved. And now that we've seen when it might not always work out, and then the Gauss-Jordan algorithm may not always work, that is all we'll have to speak for today. And just I appreciate it. Thanks for just sitting down with me and learning a little bit about the Gauss-Jordan algorithm with me. Thank you. I am Jonathan.